Hi there. This is a short presentation of the superposition theorem. Again, for your assignment, you have to calculate a problem where you've got two power supplies feeding one load, and you want to know what's actually getting into the load. So, what is the current? What is the voltage across the load? What is the current into the load? And you need to figure this out. And the ways to do this is to use DC theorems, and there are four of them, which are generally about, and they're called superposition, Norton's, Thevenin's, and Kirchhoff's. Now, superposition is probably one of the easiest theorems to use if you are very familiar with Ohm's law and you can handle it very well, but you are not so sure about all the other theorems and the little sort of the techniques you have to apply to try and get this. Okay, just to remind you what this is all about, just follow the mouse. We've got two power supplies here. We've got B1 in this instance and B2. So one is 28 volts, one is 7 volts. We've got a 1 ohm resistor, which sort of represents the internal resistance of the power supply on B2. So that resistor is called R3. And then we've got a 4 ohm resistor, which is the internal resistance of the 28 volt power supply, labeled as B1, and that comes with 4 ohms. Yeah. Again, just to remind you, what is an internal resistance and what does it stand for? Yeah. So when you connect a load to a battery or to any power supply, what you'll find is almost inevitably is that the voltage is going to drop a little bit. Yeah. So it's going to be a tiny bit of a voltage drop. And depending on the current you draw out of it, sort of the bigger the current, the higher the voltage drop. So even a car battery, so if you turn on your, let's say your car battery is on 12.5 volts or something, and you turn on your lights, it's going to drop down to, the battery itself is going to drop down to about 12 volts. Whilst there's a current of about 4 or 5 amps coming out of the battery. Now, the voltage drop, it's very straightforward. You've got a current flow, you've got a voltage drop. The voltage drop happens inside the battery, so there must be some sort of hidden internal resistance. We can't see it, it's not a resistor, it's nothing that is tangible, so it's some sort of hidden resistance. Yeah? And that is sometimes, when you look at these circuits, that is what's represented with these circuits. Just to give you a warning, that resistance is not a constant value. The more current you draw, it seems to change. I did some tests on various batteries. And you can try it out yourself. So if you can actually calculate it. So if you draw 1 amp out of a battery, you get X amount of voltage drop. Then you draw 2 amp out of a battery, and basically the current, I times V divided by the current. So R is equal to V divided by I. So you can work out the internal resistance. So if you draw 2 amps out of it, what you find is that value is actually going to change. Yeah, it's not a constant. So again, it's something to bear in mind, bear in the back of your mind. But anyway, that's what this represents. Then in the middle here, we've got with 2 ohms, R2, that's our load. That's where the power in both instances goes in. Now, what does this represent? It's this stuff in everyday life. I mentioned this before, but let's do it again. It could be just the electricity or the power supply you find in a car. Yeah, you've got a running engine. You've got your own little power station, which is the alternator. The alternator produces, I just checked it out outside yesterday actually, 14.6 volts. Mine, it should produce about 13.8 or 14.1, that's a nominal value. Then you've got your battery, which should stand at about 12 volts, maybe 12.5 volts, depending whether it's fully charged or not. And then you've got in both, the alternator as well as the battery, you've got a little bit of an internal resistance depending on the current that you pull out of it. And then you've got all the consumer units. That's a load, represents a load. So you've got your ECU in your car, you've got your ignition, you've got your your controls, your lights, heated rear winds or heated rear screen. You may have your fan blowing, your internal heaters blowing, lots of other stuff in the car. So that represents your load. And so you've got all these components in there. Yeah. So for example, alternator you know, with this internal resistance battery with the internal resistance, and then you've got the load itself. Another good example from everyday life is your mobile phone. Yeah, you put it on charge and you've got an external power supply which is going to supply it with 5.6 volts, 6 volts or something, a little bit more than the 5 volts. Is it about 5.1, 5.2, around about there, yeah. And then you've got your battery, which is inside your phone, which operates at about 3.6 volts, and a lithium cell, and then you've got your phone itself, which is a load, and again, your charger as well as your battery. There's some sort of internal resistance in there as well. And again, what you want to find out is there are a couple of scenarios here in this setup. For example, in a car, ultimately what we want is we want our alternator to run all the modules which use electricity in the car, but also to charge the battery. So next time we're going to start the car, we've got a full battery. Yeah. And so there needs to be enough juice to go into the load, and also there needs to be enough left to supply some current to the battery. And you use these theorems to theoretically calculate whether it's happening, whether it's taking place, or whether the load is supplied by both supplies, by B1 and B2. And that's, again, something you figure out, and that's the reason why we've got these theorems. Okay, I hope I made this clear. So we're going to carry on and we're going to look how superposition deals with that. Fairly straightforward, fairly easy. Okay, let's go through it. Okay, superposition takes a complex subtract, simplifies it. Circuit is reduced to several equivalent circuits using only one voltage or current source. The voltage drops and currents in the simplified circuit are calculated. The different V supply and I supply from different simplified circuits are then superimposed. Okay. All right, let's go through this. So we've got, the whole idea is we break the circuit down. So if you look at the circuit above, we split this up into two different circuits. Yeah? And each circuit will have only got either one current supply or one voltage supply. So we're not going to bother for the assignment with current supplies, but we're just going to use the voltage supplies. But if you've got a voltage supply, and you've only got one circuit, just a voltage or a bunch of resistors, we are back to box standard Ohm's law. And you do this twice. You do this once for this side and once for that side. And again, follow the mouse, once for that side and once for that side. And then you've got a different set of values, and you're just going to look at all the voltage drops and how the current flows, and that's it, You just subtract them or add them together, depending on how the voltages and currents flow, and we've done it. Okay, there's a couple of rules to do, but shouldn't be too difficult, and we're going to go through it. This is the important thing here. So just there's a note. Voltage sources are shorted out, and current generators are put to open circuit. Okay, again, when you go to this diagram here, so we've got two voltage sources. So when we produce our equivalent circuits, we start off with B1, and we short out B2, and then we're going to look at the figures we get for the circuit. And then the second circuit we're going to calculate is we're going to short out B1, and then calculate it from B2. So we're going to look into the circuit from B2 and then look at our voltage drops and current flows. And before that, we're going to look into our circuit from B1 and short B2 out. So it's fairly straightforward, and once you've done it, it's not that hard to do. You just need to, get all the relationships right. How is the voltage dropping from right to left or left to right? Which way does the current go, and so on. Now, this presentation has been taken from a website. It's allaboutcircuits.com, so you can check it out. There's one problem. The current is explained as electron flow and not conventional current flow. So Americans, they love to do this. So when you look at current flow, again, the whole idea is, here in Europe, we always say the current flows from plus to minus. And this is all down to theories which were developed in the 1700s. And eventually they found out that electrons actually carry a negative charge. So the current actually flows, or the electrons flow from minus to plus. And so for some strange reasons, a lot of Americans, they love to explain things with current flow or electron flow. Sorry, not conventional current flow, but electron flow. And so we get like different concepts. So to not get too confused, and maybe I should have chosen a different diagram, but just imagine all the arrows point the opposite way around than to the way you see them. Or bear in mind, this is electron flow. It doesn't really matter whether you use electron flow or conventional current flow, providing you use it consistently throughout your concept. Whatever you're doing. I think the only time here in Europe where we need to use electron flow is when we are discussing semiconductor theory. And then you come to a point where, because you're talking about positive and negatively doped material and protons and electrons and holes and excess of electrons, at that point you have to explain it from electron flow. So the current seems to go the opposite way around. That's the only way where we really need to use it. Otherwise we are pretty happy sticking with conventional current flow. Again, they're just models anyway, so that's something to bear in mind as well. Okay, let's move on. So we've got our circuit here. Again, when you just look at this circuit, you can see you've got a fairly small resistance here, a fairly small voltage here. You've got a very big voltage here, and also in in contrast, fairly small resistance. So where is the current going to go? Is there anything going from B2 into the load, or is it just B1 pushing current into the load and into B2? We don't know, but we need to figure this out, and it's very difficult to say. When just looking at the circuit, I couldn't tell. I would, because the voltage is fairly high, I would think that there's a current being pushed into B2, and that B2 doesn't push any current into the load, but that this is a major current. And again, that's a little bit of a mystery, and just using Ohm's law on its own, without a theorem, it's impossible to figure out. Not impossible, but very, very difficult. Okay, we're going to look at the first simplified circuit. So bear in mind, in this instance, we're going to short out B2, which is on this side here. And what you find is we've got these two resistors in parallel. So we've got R2 and R3 in parallel. So we're going to get about 0.6 ohms. And then we've got 4 ohms here, so we get about 4.6 ohms in total for the whole resistance, so we can calculate the current. Once we've got the current, we can calculate all the voltage drops across these resistances. And again, the voltage drops, this side is going to be more positive than that side. Same here, that side, more positive than that side more than that side. And then it goes down to earth. And I'm going to go to the next slide. And you can see this here, what we have. Again, you can see the American circuit symbols. They are resistors for Americans. We use different circuit symbols, but it's just something to bear in mind, that there are different standards, slightly different ways of explaining things. But if you understand how, then it doesn't matter what book you pick up, whether it's from this side of the Atlantic or the other, you can follow it through. E stands for electromotive force, so that's voltage. You can see this here as well, volts, amps, and ohms. Shall we go a little bit more international? You find that very often when you look at German textbooks, you get the letter E as well. It's not just Americans, Germans as well. Over here, we tend to use V for volts. Okay. So what have we got here? We've got 28 volts. We've got a current which is going through. So we calculate the current. And again, you can see it goes the opposite way around. We would say the current would go through here, then split up here, then some of it would go down here, and some of it would go down there. So anyway, we do Ohm's law, calculate all the currents, and then we put this into our table. And it's very, very important to memorize or to remember which way the plus and the minus goes around for each resistor. Same here as well with the load. So they either are together or they subtract from one another. So very important. Okay, so we're going to look at the next circuit. So that's the second simplified circuit. So we're going to short out the power supply B1, which was 28 volts, and we've just got the other one, B2. And then again, we've got the 1 ohm resistor here, and then the 4 ohm and 2 ohm resistor in parallel this time. We're going to do all the calculations. So that's the table we come up with. So we've got... We put it all here, but also bear in mind that the polarity is slightly different. So if you look at R1, just focus on R1 for now. So it's minus and plus. It makes sense as well. So the plus is more positive on this side than on that side. If I go to R1 to the first circuit here, where we go from the other side, it's the other way around. So it's plus there and minus there. So that means we have to subtract the voltages, yeah, because we get an opposing force from the other side, so we subtract it. Okay, so we put our table together. So we've got the voltage drop across R1, we've got the current across through R1, and then we've got the obviously the resistance as well, which we know anyway. So that's our little table. Now that's the important thing here, yeah, where we look at voltage and current of each of those resistors, and then we just superimpose them. Okay, this is the superposition where we start off with for our values, you know, with all the voltages in the circuit. So we've got 24 volts and 4 volts, and you can see that the polarity is the other way around. So we've got like a total voltage dropped of 20 volts across this resistor. Okay, then we've got R3. Let's have a look at R3. Where's R3? It's down here. So we've got 4 volts, you know, from the 28 volt battery, and then we've got 3 volts from the 7 volt battery, yeah. And again, yeah, so it's going to be 1 volt, but it's going to be 1 volt is more positive on that side than on that side, and so that means there's actually some current being pushed into the battery. Yeah. And then we've got the load, yeah, which is here. So we've got 4 volts and 4 volts, which is pushed into it on both sides. Am I getting this right? And so we get about 8 volts in our load. Yeah. So we've got 8 volts in the load. Right, I'm just looking at the battery as well, just to make sure I got it right. Yeah, this is 4 volts higher, isn't it? The voltage drop there than the one that's generated there. Yeah, there's 1 volt is pushed into the battery, yeah. And then here we've got 4 volts and 4 volts, so that gives us a total voltage of 8 volts, which we get into the load, which is here. And again, you can see the polarity is the same, you know, for both calculations with both batteries. And therefore, we need to get 8 volts. We have to add them up. So and that's superimposing the values for voltage. Now we're going to look at the current. Again, you're going to look at the current direction. Yeah. And again, we come up with there's a subtraction here, so it's 5 amp, which flows into this circuit here. Then when we look from the 7 volt battery and the little resistor, we get like 1 amp going into this direction, but it's electron flow. So if you use conventional current flow, it's the opposite. So it's pushing it actually into the battery. Yeah. And then we've got 4 amps sort of again going down this resistor if you use conventional current flow. Yeah. Just again bear in mind electron flow goes upwards. Conventional current flow in this instance goes downwards, just the opposite direction. Okay, right, review. Superposition theorem states that a circuit can be analyzed with only one source of power at a time. And that means we can use Ohm's law all the way, not all the way through, but obviously for this circuit. And then we do these calculations several times. If you've got 3 power supplies, 4 power supplies, or whatever, we have to do it 3 or 4 times and then create this big table and add, or sum it all up. So either add or subtract, depending which way the current flow goes, or which way the voltage drops are. The corresponding components, so let me just go through the text. The superposition theorem states that a circuit can be analyzed with only one source of power at a time. The corresponding component voltages and currents algebraically added to find out what they do with all power sources in effect. Okay, to negate all but one power source for analysis, replace any source of voltage batteries with a wire and replace any current source with an open circuit. Okay, that's one rule, and you find this for the other circuit theorems as well. So you get a voltage source, you short it out, you get a current source or current generator, you put it open circuit, and then you do your calculations. Right, I hope this has helped. I would say, that was the last slide, I would say that superposition is probably the easiest way to crack a problem of this caliber. What you need to do is, I think in the assignment states that you have to choose two theorems. So make sure you choose another theorem, either Thevenin's, Kirchhoff's, or Norton's, and then resolve a problem using that. Okay, that's all. Thanks for listening.